All right, let's go over the section 7-1, starting out topic 7. Topic 7 is all about similarity, which is a little bit like congruence. When we did our triangle congruence section, we had our angle side angle theorems and things like that. We're going to go back to that idea, but we're going to look at similarity. So we'll get into what is similarity in the next section, but here we're just going to talk about one more kind of transformations. Back when we did our transformations unit in chapter 3, we talked about our rigid motions, which were the translations, reflections, and rotations. This is a different kind of transformation that is not a rigid motion. Remember, rigid motions leave things congruent to the way they were. They're the same size and shape as they used to be. Dilations don't do that. Dilations are a type of transformation that makes a shape larger or smaller. And that's what we're going to be looking at today. We've got a couple new vocab words in this definition that we'll go through as we go here. So a dilation is a transformation that changes the side lengths of a shape, that changes the side lengths of a shape according to a scale factor. That's how we know how big or small to make the shape. So according to a scale factor with a given center of dilation. That's another vocab word that we're going to use. Center of dilation. Where are we making the thing bigger or smaller from? So a couple of vocab words in here. We've got scale factor and we've got center of dilation, and we'll talk about what both of those mean. The other thing that I want you to write down about a dilation is that it can be an enlargement, making something bigger, or a reduction, making something smaller. And the scale factor will tell us which one it is. Example 1, we're going to really just kind of talk through. I'm not going to make you do example 1 because that would require rulers, and it's really not that important. So this is just showing you how dilations work. If we were going to take this shape, the pre-image, which is ABC, and it says dilate triangle ABC by a scale factor of 1/2. If our scale factor is less than 1, our shape is going to get smaller with fixed center P. So the center of dilation is P. What that means is the distance from every point in the first shape, in the pre-image, to P is going to get cut in half. So where BP was maybe 8 centimeters long, B prime to P is 4 centimeters long. From A to P is going to get cut in half, and from C to P is going to get cut in half. And that's going to give us our new shape, A prime, B prime, C prime, which is half the distance to point P, and it's also half the size of ABC. So just by coincidence, or not really coincidence, but by mathematics, AB is twice the length of A prime B prime. Or said the other way, A prime B prime is half the length of AB. So it's a dilation with a scale factor of 1/2. We can also dilate a different way. This would be a dilation if the center of dilation was inside of the shape. And in here, the center of dilation is point Q, which is inside the pre-image WXYZ. This one says dilate by 2, so the scale factor is more than 1, which means that the shape is getting larger. The distance from the center to point W gets doubled. The distance from the center to point X gets doubled, and so on and so forth. And then when we make the new shape with those doubled points, not only is every point in the new shape twice the distance from Q, every segment in the new shape is twice as long as the segment in the old shape. So this shape is twice as large. So we can do that if we want to with a ruler and making these 3 times longer or 1/3 as long. We're going to skip those though. We're going to go right to the stuff we don't need to do with a ruler, which is example 2. So in this example, it says rectangle A prime, B prime, C prime, D prime, the image is a dilation with a center of P of rectangle ABCD. How are the side lengths and angle measures of ABCD related to those of A prime, B prime, C prime, D prime? So let's look at the side lengths. AB has a height of 3, and A prime, B prime has a height of 9. AD has a length of 2, and A prime, D prime has a length of 6. So it looks like the side lengths are 3 times as long. So we can say side lengths are 3 times as long. However, when we look at the angles, we notice that both of these are rectangles. And we can't change the measure of the angles in a rectangle without it not being a rectangle anymore. So they must have the same angles. And that's actually something that we'll come back to over and over and over this chapter, is the angles are going to stay the same even when the side lengths get longer or shorter. All right? We can also look at how those side lengths are getting longer and shorter and be able to find the scale factor that is the scale factor of the image. So in this first example, we don't have a grid, but we do have some side lengths. We know that KL is 12 and K prime L prime is 18. So immediately we know the scale factor is bigger than 1 because our shape got bigger. What we can do is we can take the the new shape, length 18, divided by the old shape length 12, and we can find the scale factor that way. So 18 divided by 12 is 3/2 or 1.5. So this is a dilation of quadrilateral JKLM with scale factor of 3/2. In this next picture, we have these two shapes, and we have a center of dilation, in this case, that's outside the shape. You can kind of tell because A prime, B prime, C prime is closer to P. So it's moved closer to a certain point. It's moved closer to its center of dilation. We can look at the scale factor a couple of ways. We can look at the distance from each of these points to the center of dilation, or we can just look at the length of the sides. So AB has a length of 2, but A prime, B prime has a length of 1. Once again, we're going to do side length of the new shape divided by side length of the old shape, and we find that the scale factor of this dilation is 1/2. There's a few different ways that we can dilate depending on the center of dilation. When the center of dilation is the origin, it's really easy and methodical to do a dilation because all the points in our shape are going to be multiplied by the scale factor because they're going to be further away or closer to the origin point, which in this case is 0, 0. So when it says, what are the vertices of a dilation of 1/4 of triangle PQR, notice that there is nothing after 1/4. Since there's nothing after 1/4, that means the center of dilation is the origin. If there's something there, that thing would be the center of dilation. But here there's nothing. So all we need to do is take each of the 3 points that we have, multiply them by our scale factor, and that'll give us our 3 new points. So here are our 3 original points, right? P is at 8, 4. Q is at 12, -4. And R is at -4, 0. And what we'll do is we'll find P prime, Q prime, and R prime by taking 1/4 of each of those measurements. So 1/4 of 8 is 2, 1/4 of 4 is 1. So P prime is at 2, 1. For q prime, that's going to be 1/4 of 12 is 3. 1/4 of -4 is -1. So q prime is at 3, -1. And r prime then would be at -1, 0. So there's r prime. Then all we need to do is connect the lines together and make our dilated shape. And as you can see, each line, each side length in the new shape is 1/4 of the corresponding side length in the pre-image. So that 1/4 is shown by distance to the center of dilation and also length of the sides. And actually, I think that's what this question is asking. It says, how are the distances to the origin from each image point related to the distance to the origin from each corresponding pre-image point? For example, the distance to the origin of point R is 4 units. The distance to the origin of point R prime is 1 unit. So they're all proportional to the scale factor. The distance from O to P is 4 times the distance from O to P prime. So what we can write is the distances are 1/4 of the original distance, and they're always proportional. They're proportional to the scale factor and to one another, always proportional. And that idea of the distances are a certain fraction of the original distance, that happens whether the center of dilation is the origin or not. So here we're going to look at an example where the center of dilation is not at the origin. It says, what are the vertices of a dilation of scale factor 1/2 with center of dilation R of QRST? So what that means is if the center of dilation is R, all the points in this image are going to be half the distance to R than they used to be. So for right now, the distance from R to S is 6 units. That means the distance from R to S prime is going to be half of that, but it'll be in the same direction. So S prime is only going to be 3 units away from R. The distance from R to Q is 1, 2, 3, 4, 5, 6, 7, 8 units. So the distance from R to Q prime is going to be half of that, or 4 units. And I could find the distance from R to T by doing the distance formula this way and finding half of that. Or I could say, wait, I'm going to dilate a rectangle. It's still going to be a rectangle. And I can just find the coordinates of T prime by knowing my shape is still going to be a rectangle. And then I have my new shape. And see how when the center of dilation is not the origin, the shape sort of shrinks down towards the center of dilation? That's how things are going to work. It's getting closer. Every other point in the shape is getting closer to the center of dilation. If the scale factor was more than 1, every other point in the shape would be further away from the center of dilation. But since this is 1/2, it's going to be getting closer. Here it says, what is the center of dilation and the scale factor of the figure at right? So I can see that my image is the orange one. My pre-image is the black one. So it went from A, B, C to A prime, B prime, C prime. I know that my scale factor is greater than 1. I can figure out the scale factor by sort of looking at the lines that I have on the graph. So if I look at AB, that goes up 2 over 1. And if I look at A prime, B prime, that goes up 3 over 1.5. Or I can see how the distance changes. Here's A to B's distance, and then B has kind of like 1/2 more than that amount. I could use the distance formula as well to figure this out more mathematically, but I'm just kind of looking at these points and finding out how the length of these lines has changed. And in doing so, I find the scale factor. The scale factor here would be 3/2 or 1.5 because A prime B prime is 1.5 times as long as AB. Or A prime C prime is 1.5 times as long as AC. So I can kind of use that information to give me the scale factor if I didn't want to use the distance formula to find out exactly how long each of these sides are. And then the center of dilation is pretty easy to see as well, because the center of dilating, the center of dilation is the spot the shape is growing from. It's also the point that does not change between the pre-image and the image. So that center of dilation is going to be point A. We're growing away from point A as we go. Finally, we're going to use a scale factor in order to take a real-world problem and scale it up or down, do a dilation in the real world. In this case, we're looking at blueprints because blueprints are a scale drawing, a much smaller drawing to a real thing, in this case, a kitchen. Could be a kitchen, a house, whatever. And it says a blueprint for the house uses a scale factor of 1/20. So compared to the real house, every distance on the blueprint is 1/20 as long. If the dimensions of the actual kitchen are 3.1 meters by 3.4 meters, what are the dimensions of the kitchen on the blueprint? So all we need to do is we need to take these dimensions and multiply them by 1/20 and or divide them by 20. So I would take 3.1 meters, divide it by 20 to get its length on the blueprint. So its length on the blueprint would be 0.155 meters. I would take the other dimension, 3.4 meters, divide it by 20 to find the dimensions of the kitchen, or the other dimension of the kitchen on the blueprint, which would be 0.17 meters. Okay? And those would be the new dimensions. So the dimensions of the kitchen on the blueprint would be 0.155 meters by 0.17 meters. Honestly, that would probably be more useful as centimeters because 0.155 meters is 15.5 centimeters and 0.17 meters is 17 centimeters, but that's all right. This next question is really important. This is asking us not about the dimension of the kitchen, but the area of the kitchen. This is a relationship that we're going to learn about dilations that's going to be important for you to remember and important to be able to use in problems. Because even though the dimensions change by a factor of 1/20, the area is going to change in a different way. So if I am looking at the area of these two kitchens, the real one and the blueprint, the real one, and let me make that look a little bit similar there. No? Can I not? Oh well, we'll have to pretend this is to scale. So the real kitchen is 3.1 meters by 3.4 meters. And the blueprint kitchen is 0.155 meters by 0.17 meters. We know that to find the area, we do length times width. So the area of the original kitchen is 3.1 times 3.4, which gives us 10.54 meters squared, right? Square meters for area. The area of my blueprint kitchen, when I multiply those together, is 0.02635 meters squared. Now that is not a 1/20 relationship. That isn't 10.5 divided by 20. That's 10.54 divided by something else. So to figure out the scale factor between the areas, let's do 10.54 divided by 0.02635 meters squared. When we do that, we get 400. So that means the area is 400 times bigger on the original kitchen. Or 1/400th on the blueprint. So if I took my original kitchen, multiplied by 1/400th, that would give me the area of the new kitchen. How is 1/20th related to 1/400th? Well, if I took this kitchen and I made each dimension 1/20th of the length, and then I multiplied them together, I would also be multiplying my scale factor of 1/20th for the width times my scale factor of 1/20th for the height to give myself a scale factor of 1/400th for the area. I squared the scale factor when I squared the dimensions of the figure to give me the area. Since area is a square unit, my scale factor gets squared. Okay? If I showed you a different one, what if I gave you another example where I have a room or a shape that is a 3x4 rectangle, and I have a room that is going to be bigger by a scale factor of 3. So this would be a 9x12 rectangle. That 3x4 rectangle is going to have an area of 12. That 9x12 rectangle is going to have an area of 9 times 12, or 108. And that ratio of areas, if you think 12 times what is 108, that ratio of areas is 9. So our scale factor is 3, and the ratio of areas is 9. 3 squared is 9. So what we can write down, what we can internalize from this, is that the ratio of the areas, specifically areas, is the scale factor squared. What do you think that would mean about the ratio of the volumes of two shapes? I'm not going to tell you. I just want you to think about what that could mean for the ratio of volumes of two shapes. All right, and that's everything for this section. You can go ahead and work on the work that goes along with it. All right, thanks so much, and have a wonderful day.